Yeah, so this is a two-part talk. I will do a gentle introduction to a bunch of techniques that we've been developing with Jeff, and then he will explain the background, and he's going to explain in detail how to use them. Okay. So we are going to be working on a compact manifold. So M is a compact Riemannian manifold, and throughout the talk I'm going to denote by little n the dimension of the manifold. On the manifold, we are going to work with Laplace eigenfunctions, and I'm going to denote them by Th. And since we are going to be studying the growth of these eigenfunctions, we need to choose a normalization, and that normalization throughout the talk is going to be that their L2 mass is 1. Okay. So the manifold is compact, it's smooth, it has no boundary. That's this first line here. And the second line is just what our eigenfunctions are. And this is just in case you need motivation, further motivation to work with eigenfunctions. So you can think of an eigenfunction as the quantity giving you what's the probability of finding a quantum particle of energy h to the minus 2, so the eigenvalue for the eigenfunction at the point x. So this gives you a probability density, and all the plots that I'm going to be showing today are actually for this probability density. So I'm plotting the absolute value of the eigenfunction. So the idea is to try to understand how eigenfunctions concentrate in different parts of the manifold. And mainly, the goal is to try to keep track of how eigenfunctions respond to different geometric setups. So how do they respond to how the geodesics that emanate from X behave? And so we believe that all the geometric and dynamical properties of the manifold can be recovered through the eigenfunctions. This is just to illustrate how they keep track of the geodesic flow. So you have two manifolds here with boundary. You have the disk and the cardioid. And in red, what you have is the trajectory of a classical particle if you just kick it with some initial velocity and it starts bouncing around. So here, the classical particle avoids the center of the circle altogether, while here in the cardioid, where the geodesic flow is chaotic, the particle ends up filling the cardioid. And the counterpart to this are these eigenfunction density plots. So again, this is the absolute value of the eigenfunction, the modulus. In black, what you see is where the eigenfunction takes a high value, white means the eigenfunction is 0 there. So the way in which you should read these four plots, so these plots are eigenvalues growing in this direction, is that the probability of finding the quantum particle here near the center of these disks is 0, reflecting what was happening with the classical particle. While here in the cardioid, the probability of finding the quantum particle here in any portion of the cardioid seems to be proportional or completely determined by the area of the that you're trying to understand. So if you want to know what's the probability of finding the quantum particle in half of this cardioid, it looks like it should be half. And the only symmetry that this cardioid displays is just this axial symmetry, but otherwise it seems like the chaotic behavior of the geodesic flow is also reflected by the density plot of the eigenfunction. So basically what we are going to be doing today, my talk, is divided in two parts. In the first one, we are going to fix a point here on the manifold, and we are going to try to discuss what happens when you evaluate your eigenfunction at the point, and then you let h go to 0, so the eigenvalues are growing. And in the second part of the talk, what we are going to do is to do something slightly more refined. We are going to fix a submanifold, h, and then we're going to average the eigenfunction along this submanifold and try to understand what happens with these eigenfunction averages. throughout the talk, I'm going to list several results to showcase how robust the techniques we've been developing are. But what you should take out of this talk is not the results, but the techniques, how we've been working with eigenfunctions and trying to understand how they concentrate. And now that I said that, I should also mention that this is not only what we've done doesn't only work for eigenfunctions of the Laplacian. It works for quite weak quasimodes of elliptic self-adjoint operators. And what you should do if you prefer to think in those terms is to replace geodesic flow everywhere by Hamiltonian flow. Every time that I say geodesic, just think of a bi-characteristic. OK. So I'm going to start with the first part of the talk, which is about supremum norms. So how large can the value of the eigenfunction when you evaluate it at the point x be? And in order to do that, I have to talk about the enemy. The enemy for this problem are Sonal Harmonics. So Sonal Harmonics, and again, this is the density plot of a Sonal Harmonic. So this is the absolute value of one. What they do is they blow up at the south and north poles. So here is your sphere, and here they are quite big. So if I'm working in S2, this is like h to the minus a half. And what happens with the sonals is that the eigenfunctions, they are going to grow like h to the minus n minus 1 over 2. So remember, throughout the talk, n is the dimension of the manifold. And the point is that this is the extreme behavior. I'm going to be always comparing against the sonal throughout the talk. And the reason why this is extreme is that in general, we know that eigenfunctions cannot grow more than h to the minus n minus 1 over 2. So Sonal Harmonics actually saturate this upper bound, proved by several people, Levitt and Abakumovich, Hormander. And I'm going to record it here because this first part of the talk is about trying to improve this upper bound under different geometric assumptions. So OK. So how do you go about improving this? Sogtov and Seldich improve it to a little low if they ask that the set of recurrent directions at x has measure 0. So you fix your point x here, and you look at all the directions that for which the geodesic loop will bring you back to the point x infinitely many times and arbitrarily close to the direction that you started with. So you're working in Sx star m, and here you measure the volume of the set of such directions. If that volume is 0, then they get this little low improvement. And this result was recovered by Jeff 2 years ago. And the reason why I'm highlighting this is because it is this paper, the one that kickstarted the line of work that I'm going to present to you. So in this paper, Jeff recovered this little low under the assumption that the volume of the set of recurrent directions is 0 using the effect measures. So when Jeff was working on trying to understand subnorms using the effect measures, at the same time, John Toth and I were working on understanding integrals of eigenfunctions, so averages of eigenfunctions over along curves using the effect measures. Then we joined forces, and we ended up using now the techniques that Jeff started working on in this paper to try to understand what happens with eigenfunctions. But we are no longer using, at this point, the effect measures. So the effect measures, Jeff is going to explain this in detail, but they have the disadvantage that if you want to get quantitative improvements on this error, they will not do it. The most you can hope if you're using an effect measure is a little low error improvement. So we stopped using the effect measures, and then we started trying to keep track of what happened with the eigenfunction when you were trying to, when you study them in terms of what happens with the set of geodesics that emanate from the point at which you're trying to understand the growth. So what happens if you want to get quantitative improvements on this? The most well-known result is due to Berard, and it says that if the manifold has no conjugate points, then you can get a logarithmic improvement here in the denominator on this universal upper bound. And so usually, if you see any logarithmic improvement when you're working with eigenfunctions, what's happening is that they are working under the assumptions that the manifold has either no conjugate points or negative sectional curvature, which is a subset of the set of manifolds with no conjugate points. And what that allows you to do is you work with the eigenfunction, you reproduce it using a spectral projector. You turn the spectral projector using an inverse Fourier transform into the wave kernel, and then you study the wave kernel. And what happens when the manifold has no conjugate points is that you can lift your computation to the universal cover. And in the universal cover, you have a good parametrics for the wave kernel, Hadamard's parametrics, that allows you to keep track of what happens for logarithmic times. So this is how usually they get this logarithmic improvement. But with Jeff, we did not want to get quantitative improvements under this assumption. We wanted to allow for conjugate points to exist in our manifold. We actually wanted to get quantitative improvements when I evaluate at x, and x is possibly a conjugate point. And so since I'm going to be talking about conjugate points throughout the talk, I just wanted to remind ourselves what I mean by this. So I have 2 points here, x and y, and we are going to say that x and y are not conjugate to each other if there exists a geodesic that joins them and a Jacobi field along the geodesic, such that the Jacobi field vanishes here but doesn't vanish when it gets all the way up to y. If you're not used to working with Jacobi fields, what they do is they satisfy this Jacobi equation, which probably you cannot read. But the point is that what they do is they keep track of how fast geodesics spread apart from each other, how they spread apart. So what happens is that if I start with a Jacobi field in this direction, then a geodesic that will start in this direction will wrap around my previous geodesic, spreading apart from the original geodesic as much as the Jacobi field dictates. So if the Jacobi field here is non-zero, that means that that geodesic is going to be moving apart from the point y once you get all the way up to y. So that's what Jacobi fields do for you. And in a sense, the sphere is the worst case scenario for conjugate points. So what happens on the sphere, on the two sphere, is that every Jacobi field that's 0 here is going to be 0 when you get all the way to the south pole, also 0 when you come back. So actually, every point is self-conjugate on the sphere. But something even worse happens on the sphere, and I want to make a point of this, which is that every point is maximally self-conjugate. So what I mean by this is you are trying to understand what happens with the Jacobi fields starting from a point x. And if you look at the space of Jacobi fields that are not tangential to your geodesic, this is a space with dimension n-1. And what happens on the sphere is that you have n-1 linearly independent Jacobi fields that vanish here and also vanish when you return. That means that you are maximally self-conjugate. In every single direction that you start on the sphere, when you come back, your geodesic is closing. And that's going to be the enemy, actually, if what you want to do is to saturate this upper bound, to be maximally self-conjugate. So the first result that we were able to prove is that if you work with points that are not maximally self-conjugate, then you can always get this little low improvement on the universal upper bound. And by that, what I mean is that if I start at a point x and I return to it after some time t, I'm not maximally self-conjugate if there exists a Jacobi field that will not vanish when you return to the point x. So there is at least one direction in which my geodesics are spreading apart. If you ask for something slightly stronger than this, and what you do is, instead of looking at the geodesics that actually come back through the point x at time t, you look at those that get exponentially close. This says e to the minus constant times t. If I come exponentially close to the point x, then if you ask that not all the Jacobi fields will vanish in that tiny segment near your point, then we can get the logarithmic improvement. this condition we are calling uniformly maximalist of conjugate. And this, to our knowledge, this is the first result that gets a quantitative improvement at the point x, allowing the point x to be conjugate. It can be self-conjugate. It just cannot be self-conjugate with maximal multiplicity. And what I'm going to do for the rest of the first part of the talk is to discuss, so first I'm going to explain what are the techniques behind proving a result like this, and then I'm going to give you an idea of how to actually get this bound. But Jeff, in his talk, he's going to talk about a more general case where you're working with manifolds with an also geodesic flow, and you can get slightly stronger results there. OK, so what are the techniques that we are using? How do we study the growth of an eigenfunction at a point x? What we are doing is, or what motivates what we are doing, it's the Sonal Harmonic. So if you look at the Sonal Harmonic and you know that it blows up at these points, suppose what you want to do is to reconstruct what's the behavior that you're seeing. And we are going to reconstruct it in terms of decomposing it into Gaussian beams. So on the sphere, what happens is that you have this highest weight spherical harmonics. And what they do is they concentrate along a closed geodesic, so along a great circle. And the way in which they concentrate, and again, this is just the plot of the absolute value, is that along the equator, they peak like h to the minus a quarter, and the width of this band is h to the half power. And what's going on here is that along the equator, they are oscillating. The way in which they oscillate is done here in this profile. So the frequency is h, 1 over h, and this is just the height again. So you have these Gaussian beams. So they are called Gaussian beams because their decay is Gaussian. And the idea is that we are going to try, by considering linear combinations of Gaussian beams, to recover what happens with a Sonal harmonic. So let me explain what I'm saying a little bit slower. You fix your point on the sphere, and then you consider, for example, this Gaussian beam across the point. And what happens with this single Gaussian beam is that the L-infinity norm is h to the minus a quarter. And suppose you started with it normalized so that the L2 mass is 1. The behavior of a Sonal harmonic is that at the North Pole and South Pole, the growth is h to the minus a half. So this is quite far away from what we want if you want to saturate this upper bound. So you go ahead and you put a second Gaussian beam, orthogonal to the first one. And what happens is that the L-infinity mass is going to duplicate. And you have to keep track of what happens with the L2 mass, because throughout the talk, and this is important for this part, we are working with the eigenfunctions that are L2 normalized. That's the assumption that I'm using in order to write this universal upper bound. OK, so 2 aren't enough, so you put a third one. And then we are adding 3 Gaussian beams. And you quickly realize that what you need to do in order to saturate this upper bound, or to get as high of a value at the point x as possible, is to put as many Gaussian beams through this point as you can, while still keeping them orthogonal to each other. And how many of those can you put? Well, they are supported in these bands of width h to the 1/2. So you can put h to the minus a half of them. So you do that. You go ahead and you put h to the minus a half Gaussian beams through the point x. And what happens is that they will cohere at the point x and give you back this subnorm, which is h to the minus a half, h to the minus a quarter. H to the minus a half is just the number of Gaussian beams that you put through the point. And h to the minus a quarter is the height of a single one of them. So you kept track of what was happening with the L2 mass. Since they were orthogonal to each other, the L2 mass is now growing like h to the minus a quarter. So when you normalize your problem so that your eigenfunction, the one that you're building as a linear superposition of these Gaussian beams, has L2 mass 1, you are dividing this number by h to the minus a quarter, so you get back the h to the minus a half. which is this growth that the Sonal harmonic was showing you. So we wanted to saturate the upper bound, this universal upper bound. And what you realize is that you have to put these Gaussian beams that are going to be uniformly distributed in the set of directions that emanate from X. If you look at it from the point of view of using the effect measures, what that means is that the effect measure needs to be supported in a set of directions that's going to have positive mass. But if what you want to do is to get quantitative improvements, what this indicates that one should do, perhaps, is to try to understand what happens with your eigenfunction when you restrict them to each single one of these directions. Because what this Sonal harmonic is doing is being uniformly distributed across all these directions with the same mass. The L2 mass is like h to the minus a quarter. So perhaps that's what needs to happen in order for you to saturate the upper bound. Perhaps what needs to happen is that if I'm starting at the point X and I look at the set of all the geodesics emanating from X, when I restrict to my eigenfunction to each of these directions, then my L2 mass has to be h to the minus a quarter in each of these directions, or at least in a positive measure set of such directions. So what we are going to proceed to is actually do exactly that. We are going to start with a point X, and we are just going to look at all the geodesics emanating from X. And we are going to look at what happens with the eigenfunctions when you restrict them to tubes around these geodesics. And these tubes, you should think of them as the width, so as these bands where the Gaussian beams were supported. So these tubes have a radius, r of h, that's going to 0. We couldn't get all the way up to h1/2, so it has to go slightly slower to 0. And we are going to just study what happens with the eigenfunctions when you restrict them to each of these tubes with their L2 mass. Because I'm going to use this very soon. This is just to record that the volume of each of these tubes is the radius to the power of n minus 1. I'm here in the fiber, cotension fiber at X. So my dimension is n minus 1. So that's what the volume of each of the tubes is. OK. So the first result that we proved, and this is really the nice result that we proved, it works under no assumptions on the geometry of your manifold. You just fix a point X. And if you want to understand what's the value of your function at the point X, this is how you should, so you are just, this is a ball, radius RH, that's going to 0, and center at the point X. So think of this as evaluating your function at X, the absolute value. We could control it by this quantity. So let me parse what this quantity is for you. So this first term here, constant times h to the minus n minus 1 over 2 is just this universal upper bound. But then what we are doing is we are weighing this bound by this quantity here. So we have the radius to the power of n minus 1 over 2 times this sum. So let me now explain what that sum is. So to build this sum, what we did was we fixed the point X. We consider all these tubes emanating from X of radius r of h. And then we are microlocalizing the eigenfunction to each of these tubes. So we are decomposing the eigenfunction as a sum of as many pieces as tubes you have. And then what this is just the sum of the L2 masses of the eigenfunction when you restrict it to each of these tubes. So a priori, you may say, OK, this is a nice result, and it works under no assumptions. But how do I actually go about using it? And
so how are little r of h and big R of h related?
When we work, we think of both of them as being h1/2. But r of h for this result just needs to go to 0. And big R of h is just h to the 1/2 minus epsilon. OK. So you look at all the tubes emanating from the point X, And what you're going to do now is you're going to classify them in two categories. You're going to work with good tubes and bad tubes. And what we are going to do is we are going to call a tube good if what it does is that it's not self-looping for logarithmic times. So you look at your tube and you're going to say this one is good in the sense that it belongs to this green team if after a log h inverse time, it doesn't loop back. And if you do that, then you can rewrite this estimate as the following upper bound. So here you have a constant times h to the minus n minus 1 over 2, which is the same quantity as appearing here. Here you have the radius. And then here you have the sum of the L2 masses. And this sum of the L2 masses, you can rewrite it as the number of bad tubes to the power of 1/2 plus the number of good tubes to the 1/2 divided by logarithm of 1 over h. Jeff is going to explain these two results in detail, how to get to those. But what I'm going to do in this slide is just to give you a nice picture of why is it that they work. The way in which you should think of this second result is in terms of volumes of set of good directions and bad directions. Remember that I was telling you in the previous slide that the volume of a single tube is r to the power of n minus 1. Then what happens is that when you put these two terms together, the radius times the number of bad directions, you just get the volume of the set of bad directions that are looping back to the point, plus, and then you have this logarithmic improvement on the set of good directions, which hopefully are most of them. So the ideal situation, if you're trying to use this result, is that for some reason you can look at the geometry happening with the geodesics that are emanating from x, and for some reason you can actually say, well, the set of bad directions emanating from x has very small volume. So I have very few directions that are going to be self-looping for log h inverse times. And then you get a logarithmic improvement immediately if this term is small in comparison to this one. What happens on the case of the Sonal harmonic is that the set of bad directions is everything. So you just get you get no improvement. This term is not there. The reason why one can go from this estimate to counting number of good and bad directions is Egorev's theorem. And again, Jeff is going to explain this in detail, but I'm going to just show you a picture to give you what the idea is. So you start with a single tube. And what happens is that the L2 mass of your eigenfunction restricted to that tube is going to be controlled by the total L2 mass. And now this tube, what you're going to do is you're going to propagate it once. And if the tube is not self-looping for time 1, then what happens is that this mass, by Egorev's theorem, is duplicated. And so twice the mass of a single tube is controlled by the total mass. And you can keep going doing this log h inverse times if you're not self-looping for log h inverse times. And what that means is that then when you're looking at the mass of a single tube, you can give an upper bound in terms of the total mass divided by this logarithmic improvement, which is what's appearing here. For this set of good directions, the ones that are not self-looping for log h inverse times, you get this log h inverse improvement. Okay, so what I'm going to do in the next slide, which is the last one for the for subnorms, is to explain how to use a decomposition of this sort into good tubes and bad tubes to prove this result that I was talking about at the very beginning about points that are not maximally self-conjugate, how you can get a logarithmic improvement at a point x if you know that not all the directions will generate geodesics that will close at x. So that's this slide, how to build good and bad tubes if x is not maximally self-conjugate. Okay, so this is just the statement that we had in the previous slide. I just wanted to put it up there so that you kept in mind what we were doing. We are building these tubes, the good ones and the bad ones. And in this picture, my manifold has dimension 3. So the set of unit directions emanating from X is a sphere. And I'm unfolding the picture because otherwise drawing this was tough. This is X, and this is X again, okay? I'm looping back at X. And the point X, remember, the condition on it was that it wasn't maximally self-conjugate. So there exists a direction, this direction namely, along which there is a Jacobi field that starts being 0, but here it will be not 0. So in that direction, geodesics are spreading apart from each other. You have the existence of this one direction. And what you will do once you have this direction is you're going to zoom in here, and you're going to try to build your good tubes and bad tubes. So how do you go about that? So this is just this purple geodesic gamma that was joining X with itself. That's this direction. And this green arrow is the initial direction for the Jacobi field, and this is just the orthogonal direction. And what you know is that if I start with a geodesic that has any component, that has a component in the green direction, then that geodesic will not loop back. At most, there is this single direction, the orange one, that's perpendicular to the original one, where if I start in that direction, it may be that my geodesics close when I come back all the way back to X. But what happens is that this is a closed condition, right? Like I only have one direction in which things may close. So what I can do is I just cover that direction with what I'm going to call bad tubes. And these are going to be small in number because it has codimension 1. And then everything else I'm going to declare to be a good direction, because I know that if I start with a geodesic that's centered in any of these tubes, then that geodesic is going to wrap around my original one, but ultimately when I come back to X, it's going to spread apart from it. And this is how you manage to build a set of good tubes and bad tubes in such a way that this first term is very small in comparison to the total volume. So this term here is going to be negligible. And then you get this log improvement. You can think of these directions as being almost everything. So this is just one example about how you go about building these families of good tubes and bad tubes. Jeff is going to give you more. What I'm going to do for the rest of the talk is to talk about averages. So this is just the result that we were trying to prove. You get this lambda improvement, log H inverse improvement on this upper bound. Okay. So if you're ready, I'm going to move to averages. Is that okay? Are there any questions about the previous part?
I was curious, from your point of view, how this log H inverse scaling comes up naturally. Is it?
Why log H inverse? Yeah. It's because we are using Agorov's theorem. So we need to be able to say that if I propagate a tube, then I have control of the mass of this propagation as long as you don't self-intersect. And we are working on general manifolds, so we only can propagate for log times. But this is a very good point, actually. If you were to work on a manifold where you can actually control what happens with the masses of these tubes, if you're not self-looping for times t, and Jeff is actually going to take this point of view in his talk, then you get a t improvement instead of a logarithmic one. So it really depends on the geometry and how you can keep track of what happens with your tubes. Yeah. Okay. So averages are just one a generalization of evaluating an eigenfunction at a point. So here, if you want to evaluate an eigenfunction at a point, you just pick your submanifold to be the point. And that's actually the reason why all the techniques that we've been working with extend to this case. So now you have a submanifold, a closed, smooth submanifold, and you want to try to understand how do these eigenfunctions will average when you restrict them to the submanifold. So if you're working with a surface and you have a curve on the surface, you have these eigenfunctions oscillating like crazy. So what one should expect is that most of the time these averages should go to 0. But it really depends on which curve you pick to start with, or what are the eigenfunctions that you're working with. How do these eigenfunctions behave with respect to the curve that you're trying to study? And that's this slide. This slide is just a warning. This is an example on the two torus, where what happens is that the averages will not go to 0. So on the two torus, I'm writing x1 for these coordinates, x2 for the y coordinates. And what happens is that you can consider this closed geodesic, x1 is 0. And you have all these eigenfunctions, e to the I x1 over h. And all of them, when you evaluate them at this curve x1 is 0, what happens is that all of them are 1, constant equal to 1. So if you average the sequence of eigenfunctions along this h, what you get is the length of the curve h. These averages do not go to 0. So what this slide is here for is as a warning that it really depends on how the sequence of eigenfunctions you're working with behaves with respect to the submanifold that you're trying to study. And what we are going to see is actually what the problem with this example is that all the eigenfunctions in this sequence are concentrated in the conormal directions to the curve h that we are working with. And those are actually going to be the examples that are going to saturate what's the universal upper bound for these averages. So let me tell you what we know about averages in general. So in 82, 83, Good and Hedge Hall, they proved that these averages are bounded above by a constant if you're working on a surface that's a hyperbolic surface, when h is a closed geodesic. 10 years later, Steve, he proved that actually you don't need any assumptions on the geometry of your manifold or your curve. This bound is always true. So here, and I'm going to record this because I'm going to return to it. These averages, if you're working with a submanifold H of codimension K, so the codimension of H is K throughout the rest of the talk, then what will happen is that these averages are going to be bounded above by H to the minus K minus 1 over 2. Which is consistent with what was happening here, right? Like when you have a single point, the codimension is m. So it's the same result. This is just a generalization of that. So in this slide, I'm splitting it into two columns. Here are the results on surfaces. Here are the results on general manifolds. OK, so how do you improve this result? Chen and Zhou, in 2015, working with geodesics and surfaces that have strictly negative sectional strictly negative curvature, they improved this constant upper bound to a little O1. And let me remind you here that when you're working with the torus, the example that we saw here was the one that saturates this bound. So you got the length of the curve, so you just get a constant here. So this is an improvement on the general upper bound that you can get as long as you're working with geodesics and the curvature is strictly negative. In terms of quantitative improvements in this realm, Zhou and Chang, they proved that if your surface has negative sectional curvature and the curve h is a geodesic, then you can get a logarithmic improvement. And the way in which they did this was, again, by lifting the computations to the universal cover and working with Hadamard's parametrics there to get logarithmic improvements. This way of getting quantitative improvements is completely different than our approach because we are not using parametrices at all, actually. Steve does like this because he's convinced that we could rewrite our results in terms of parametrices, but we have not been able to do this, although we would like to. OK. Wyman in 2017 proved that if the sectional curvature is non-positive, then you can also get these logarithmic results as long as you impose some curvature conditions on the curve, but I don't want to get into that. I want to look at this side of the slide where you're working on general manifolds. And these are all very recent developments. Wyman proved that you can improve this universal upper bound to a little low if what you do is you work with the set of looping directions that are conormal to H, and the volume of those directions is 0. So what this means is I'm going to say that the direction is looping with respect to H if it's conormal to H and the geodesic flow brings you back to H after some time. If the volume of such directions is 0, then you get this little low improvement. And when we started working with Jeff, actually, what we did was to prove this statement, but for the set of recurrent conormal directions. So by recurrent conormal, what I mean is you start with a direction, and then the geodesic flow brings you back, being normal to H, but arbitrarily close to the direction that you started with infinitely many times. So you're recurrent conormal to H. And the way in which we proved this was using the effect measures, but this doesn't give you any quantitative improvement. So that's what actually the last 2 slides of my talk are going to be about, getting quantitative improvements on this universal upper bound for submanifolds. And I should say now that there is a result by Wyman that gets a logarithmic improvement if the sectional curvatures are negative and if the codimension of your submanifold is strictly bigger than 1. But we didn't want to impose this condition on the curvature of the manifold. So let me tell you what's happening here in the background if you're trying to study averages. And I'm going to go back to this geodesic beam decomposition that I was talking about before. So the idea is we are going to try to saturate this constant upper bound for these averages. So think that we are living in a surface. H is just a curve on your surface, and what you want to do is to saturate this upper bound. So how do your eigenfunctions need to behave with respect to your curve if you want to hit this upper bound? And so what we are going to do is we are going to try to build an eigenfunction out of doing linear combinations of Gaussian beams. And you quickly realize that what happens is that if this is your curve H, and you put one of these Gaussian beams across H, then what will happen is that you have oscillations in this direction, and those oscillations are going to be picked up by H. So you are going to get that these averages, they do indeed go to 0 along H faster than any polynomial in H. So this is actually the plot of what's going on. This is the profile of the restriction of the geodesic beam that you're running along this blue direction when you project it to H. You get these cancellations. All these things add up to 0, and you don't get anything. So if you want to saturate this constant upper bound, this is not the way to go. You have to place your beams so that they are orthogonal to H. And then at least you are going to pick up whatever mass you have under this loop. So here the height was h to the minus a quarter, the width of the band was h to the 1/2, so the area under this loop is h to the 1/4. So that's what you're picking up when you put your beam orthogonal to the curve that you started with. And 1 is not enough. I want to saturate this constant upper bound. So you go ahead and you put 2. You keep track of what happens with the L2 mass as you were doing before. And then you put as many as you can while still keeping them orthogonal to each other. So you put h to the minus a half of them. And then this is the way in which you saturate the upper bound, because now the average looks like h minus a half times h to the 1/4, but you're normalizing this by h to the minus a quarter. So I'm hitting this constant upper bound whenever I place my Gaussian beams to be conormal to H. So now the idea is that if you want to understand what happens with your eigenfunctions when you want to average them along your submanifold, what you're going to do is you're going to now study the set of geodesics that emanate from your submanifold in the conormal directions to the submanifold. So what I'm going to do now is I'm going to cover my submanifold by tubes that are emanating perpendicular to the submanifold. Yeah. And if you do that, and this is the last slide, what happens is that you can prove exactly the same statement that we had before, but for a single point. But now your tubes, they have radius RH, and again, the only difference is that if this is your submanifold, they are just emanating in these directions. So you decompose the set of conormal directions to H into these tubes of radius R of H, and then you just want to keep track of what happens with your eigenfunctions in these conormal directions to the submanifold that you're working with. So you can prove exactly this estimate, again, with no assumptions. And what this allows you to do is, again, you can split the set of tubes that emanate in conormal directions to your submanifold into good tubes and bad tubes, depending on the geometry of the submanifold that you're working with. And if you're lucky and the number of bad tubes is small enough, then you can get a quantitative improvement. So these are just some examples on which we were able to get quantitative improvements. So here is just a reminder of how different geometric settings interplay. So if I have manifolds with strictly negative curvature, then they have a no-sub geodesic flow and non-positive curvature, of course. And these two rheons, they live within the set of manifolds with no conjugate points. That's the big blob. And if, for example, you are working with a surface that has a no-sub geodesic flow, no matter what the curve h that you pick is, we can get this logarithmic improvement. So this first result, this actually Jeff is going to talk about this. He's going to explain how we do this. But this first result recovers all the results on the first column that I was showing you 2 slides ago. And again, you just do this by splitting the set of tubes that are emanating conormal to your curve h into good and bad tubes and controlling how these tubes behave. If you're working with no conjugate points, manifolds of no conjugate points, and you put the restriction that the dimension of your submanifold is controlled by m-1/2, then we also get this logarithmic improvement. In the opposite sense, if my codimension is 1, and if you're a geodesic sphere, then we can also control the tubes and get this logarithmic improvement. Or if I'm working in the intersection of these 2 sets of metrics that you can put on a manifold. So if I have a no-sub geodesic flow and I have non-positive curvature, you have to put this restriction on the dimension of h. You also get the logarithmic improvement. And last, if your submanifold is totally geodesic, you can also get it. So these are just some examples on which we were able to control the tubes that emanate from a submanifold. And just to finish, because this is the last slide, just keep in mind that everything that I said works not just for eigenfunctions of the Laplacian. You can work with an elliptic self-adjoint operator. What you have to do is, instead of studying the set of geodesics that emanate in the conormal directions to your submanifold, you have to study the bicharacteristics that emanate in the conormal directions, and you need to keep track of how they behave under the bicharacteristic flow, whether they self-loop or not, and for how long. Okay, that's about it. Thank you so much.